Hey, everybody. So if you're watching this on Monday, September 27th, I'm out today because it is Rosh Hashanah and I'm observing the holiday. So what I wanted to do here was record a video for you about constant velocity motion, specifically how to read velocity versus time graphs. You got a bit of a taste of that with problem set 2 for homework that I'm hoping you dabbled in and you can revisit tonight once you've had a little experience. So let's get on with this show. You should see some slides over here on this side of the screen, and let's look at them. So first of all, my question to you is take a look at this slide and what's happening? A series of guided questions. Let's start with this object's displacement between 0 and 3 seconds. Take a moment, look at the graph, answer it to yourself. At 0 seconds, this object's position is right here, right? The y-intercept on that graph, that looks to be negative 30 meters. And at time equals 3 seconds, we're up here at this position, which appears to be 90 meters. Let's throw in units on both those. So how far did this object displace, move from its starting location over that time? 90 meters minus a negative 30 meters, final position minus initial, 90 minus a negative 30, 120 meters. It's in the positive direction because the position started low and ended high. Take a moment and look at describing this object's motion in terms of both initial position and velocity. I'll give you a moment to think about it. Answer it in your head. You think you've got it? So the object's initial position, we previously saw that. That's that negative 30 meters. Velocity. Velocity requires you to calculate what quantity on this graph? Yeah, slope. I totally have no idea if you said it out loud, but the slope. Okay, so we need the slope of this line. I'm going to use that 90-meter position, and I'm going to calculate slope as such. I'm going to find how much the graph rises over, how much it runs. This we had already answered. This was 120 meters of displacement. And the time interval, 1, 2, 3, 3 seconds. So the change in position over change in time, that is velocity. That's uh, 120 divided by 3. And finally, let's write the equation of the line pictured on this graph right here on the side of your screen. All right, so hopefully that was a bit of a review for you. Nothing new here. In fact, we're going to have a chance to look at a couple other examples, give you some time to practice pretty independently. All right, pause this screen. Pause the video now if you need to look at this screen a bit longer. Otherwise, we're going to move on to the next one in 3, 2, 1. What's happening on this graph? I'm going to give you some wait time. You can continue to let the video play to answer the questions of what is the object's displacement over that period of time? What is a description for the object's motion in terms of initial position and velocity? And finally, write the equation of the line. I'll begin waiting now. All right, hopefully that all it matches up with what you got and feels like review of the first problem set and the stuff that we did in the last class. Let's move forward now and make sure we've got a couple of key definitions that we can agree on. So the term position, it's a location, it's where something is at. It requires a coordinate system kind of underneath. So if you pictured the tape measure in the hallway from Thursday's class, right, that established where 0 was, or the origin in that coordinate system, and it went off to, what was it, something like 30 meters down where the stairs were. So positions are typically measured in meters if we're talking in metric, or something like feet, miles, kilometers. So any kind of units that are allowed for position, our default is going to be meters. Displacement is the change in that quantity. Just a reminder that the symbol here, delta, for displacement, change in position, that implies we're talking about this, where x sub f is final position and x sub I is initial position. Time interval, same sort of deal. That is when you look at the final time on the clock and subtract from it the initial time on the clock. How much time has gone by? Velocity is officially defined as the rate of change of position. The word rate is in a physics term, in a science, physics or any science sense, rate is just any quantity that changes over an amount of time that elapses. So rate of change of position, there you go, changing position, and it's a rate because it's over a delta t. Another name for velocity, or another definition for velocity, we might call it change in position divided by change in time, or it might be displacement divided by change in time. So there's a couple variations there, but the first one is the most technically accurate. And then finally, we'll hit average velocity later. New representation. This is super important. It's a velocity versus time graph. So take a moment and look at this graph. What do you see happening? Describe it in words. Notice here that we've got velocity on the vertical axis and time on the horizontal. So this is a different graph than we saw previously. As a hint, I would say, how fast is the object moving when the clock reads 1 second? So go out to 1 second and up to the vertical coordinate. What is that value? It's 2.5, but 2.5 what? Like, what is that quantity? Look on the y-axis. Oh, it's velocity measured in meters per second. We would say the velocity of this object at time equals 1 second is 2.5 meters per second. What if you go out to 2 seconds? What's the velocity at that point in time? Go out to 3 seconds. What's the velocity at that point in time? Do you notice a pattern here? As you look across that graph, every single time on the clock is matched up with a velocity that is a constant 2.5 meters per second. But now this one is an interesting and new question for us. Can you translate this into a position versus time graph? Here, you're going to be doing this in your notes, but I'll sketch the beginning of it. Position versus time. Let's have this object start at a 0 position. At time equals 1 second, how far has this object traveled from its starting location? So 1 second. For every second on the clock, this object's velocity is 2.5 meters per second. That means after 1 second, we've traveled forward 2.5 meters. And at 2 seconds, we've traveled forward another 2.5 meters, a total of 5. And at 3 seconds, another 2.5 meters. So you should see here a linear position time graph. What's the slope of that graph? It's defined as the velocity, change in position over change in time. What we should see here is that a velocity time graph displays the slope of a position time graph. Let me write that down for you. It is a huge idea. They show the slope of the corresponding position time graph. Let's practice that a bit. Take a look at this graph. Oh, my bad, my bad. I totally got ahead of myself. This is actually the same velocity time graph. My bad. We can answer questions also about the displacement of the object, like how far has it traveled? Let's go back up here. How far had the object traveled when the clock got to, 3 seconds? 2.5 meters, then another 2.5 meters, then another 2.5 meters. That's a total of 7.5 meters. Over the first 3 seconds, that object traveled forward 7.5 meters. Can we write the mathematical relationship for this object that relates its velocity and position and time? This is a great moment for me to stop this particular recording, give you a moment to think about this, and then let you pick up with a new video. Also a good time to take a brain break in between these videos. I'll see you in the next video.